Welcome to another deep dive. Today, we're going to be tackling the theory of computation.
Okay.
Specifically, we're going to explore what a computer actually is,
Right.
like at its core.
Yeah.
You've shared some fascinating sources with me, and I'm really curious to unpack them.
It's a pretty fundamental question in computer science.
Yeah.
And to make things a bit easier to grasp, we often use simplified models,
Right.
like finite state machines,
Okay.
also known as finite automata.
Finite automata.
Mm.
It sounds like something out of science fiction.
Yeah,
But the sources suggest they're actually all around us,
that's right.
even in everyday objects.
Yeah. And what's remarkable is that even with limited memory,
Okay.
these models can accomplish surprisingly complex tasks.
Wow.
Think about an automatic door.
Mhm.
That's a classic example of a simple finite automaton in action.
Okay. I'm starting to see the connection.
Good.
The door is either open or closed.
Yeah.
Those are just two states.
Yeah, exactly. And the sensors that detect people approaching or leaving
Mm-hmm.
act as the inputs.
Right.
They provide signals like front, rear, both, or neither,
Okay.
based on these inputs and its current state.
Right.
The door's controller decides whether to change to the other state.
So if the door is closed and the sensor detects someone at the front,
Mm-hmm.
it transitions to the open state.
Yeah.
Then, if someone steps on the rear sensor while it's opening,
Right.
it stays open.
Yeah.
And once no one is detected by either sensor,
Mm-hmm.
it transitions back to closed.
You got it.
Go.
It's all about defined states and the rules that govern transitions
Yeah,
between those states
Yeah.
based on the input signals.
Got it.
That's the essence of a finite automaton.
Yeah.
And here's where it gets really interesting.
Okay.
This simple concept of states and transitions
Yeah.
can be applied to a wide range of systems,
Uh-huh.
from toll booths to vending machines.
Toll booths. So this isn't just about doors.
And not at all. Imagine a toll booth that requires 25 cents to let a car through.
Right.
This machine could have 6 states,
What?
each representing a different amount of money received,
Okay.
from 0 cents up to 25 cents or more.
So the inputs would be the coins that a driver inserts,
Uh-huh.
and each coin would trigger a transition to a new state,
Exactly.
reflecting the updated total.
Precisely.
Okay.
And here's a key insight.
What?
This toll booth doesn't need to remember the entire sequence of coins inserted,
Oh, interesting.
just the current state,
Oh, okay.
which encapsulates the total amount received so far.
That's a clever way to design a system with minimal memory requirements.
It is, and it highlights a fundamental concept in computer science: efficiency.
Okay.
To represent those 6 states,
Yeah.
the toll booth controller only needs a few bits of memory.
Wait, just a few bits. How is that possible?
Let's break it down.
Okay.
To represent 6 distinct states,
Mm-hmm.
you need 3 bits, because 2 to the power of 3 equals 8,
Right.
which gives us enough combinations to cover all the possible states.
Right.
This simple example illustrates how even relatively simple machines
Okay.
can be surprisingly memory efficient.
Okay. That makes sense.
Good.
So we've got these real-world examples,
Yeah.
but the source material also delves into the formal mathematical definition of a finite automaton.
Right?
It mentions a 5-tuple,
Yeah.
which honestly sounds a bit intimidating.
It's not as complicated as it sounds.
Okay.
It's just a way to formally describe the 5 essential components
Okay.
of a finite automaton.
Gotcha.
We've already touched on most of them intuitively, but let's lay them out explicitly.
All right, let's hear the 5-tuple breakdown.
Okay.
What's the first component?
First, we have Q,
Okay.
which represents the set of all possible states.
Mm-hmm.
Think of it like the open and closed states for the door,
Right.
or the different payment states for the toll booth.
Yeah. So Q encompasses all the possible configurations.
Yeah.
The machine can be in at any given time.
Mm-hmm.
What's next?
Next is Arcturus,
Okay.
the Greek letter sigma.
Right.
This stands for the input alphabet,
Okay.
the set of all possible input symbols that the automaton can receive.
So for the door, it would be the sensor signals.
Yes,
And for the toll booth, it would be the different coin denominations.
exactly.
All right, that makes sense.
Good.
So we've got the states and the inputs.
Yeah.
What's the third piece of the puzzle?
The third component is
Koiche.
the Greek letter delta.
Okay.
This is the transition function,
Yeah.
the set of rules that determine which state the automaton will move to
Right.
based on its current state and the input symbol it receives.
Right.
It's like the brain of the automaton,
Okay.
dictating how it responds to different situations.
That sounds crucial.
It is.
Like the map that guides the machine's behavior.
Yeah, a good way to think about it.
What about the last two components?
The fourth component is Q. Okay.
which represents the initial state of the automaton.
Right.
It's where the machine starts before receiving any input, like the door starting in the closed position.
And finally, the fifth component.
The fifth and final component is F,
Okay.
which stands for the set of accept states.
Right.
These are the states that signify a successful computation or a desired outcome
Right.
in the toll booth example.
Yeah.
The accept state would be the one where the driver has paid 25 cents or more,
Okay.
because that's when the gate opens.
Okay. I think I've successfully assembled the 5-tuple in my mind.
Good.
So we've got the states, the inputs, the rules for transitions, the starting point, and the conditions for success.
Yeah.
It's like a blueprint for building a simple computational machine.
That's a great way to think about it.
Yeah.
And we've only just begun to explore the possibilities of finite automata.
Okay.
There are different types of these machines,
Why?
each with its own unique characteristics. Oh, this is where it gets even more interesting.
Yeah.
The source material mentioned deterministic
Right.
and non-deterministic finite automata.
Mm-hmm.
What's the difference between those?
That's a great question.
Yeah.
So far, we've only talked about deterministic finite automata, or DFAs.
All right.
These are the simplest type,
Right.
where for each state and input symbol,
Yeah.
there's only one possible next state.
Okay.
It's like following a clearly marked path on a map.
Yeah.
You always know exactly where you're going next.
So with a DFA, there's no ambiguity.
Right.
The machine's behavior is completely predictable.
Exactly.
Okay.
But with non-deterministic finite automata,
Yeah.
or NFAs,
Okay.
things get a bit more unpredictable.
Okay.
In an NFA, for a given state and input, there might be multiple possible next states.
Okay.
Imagine it like having multiple paths branching out
Right.
from a single point on our map.
Whoa, that sounds a lot more complex.
It is a little bit, yeah.
How does an NFA even decide which path to take?
That's the key difference.
Okay.
It doesn't choose a single path. It explores all possible paths simultaneously.
Oh.
Think of it like having a team of explorers fanning out in all directions,
Right.
checking every possible route to see if it leads to the destination.
So instead of a single predetermined path, an NFA is like having a tree of computations,
Yes.
with each branch representing a different sequence of state transitions.
Right.
But how does it determine if it's successful, if it's exploring all these different paths?
An NFA accepts a string.
Okay.
That is, it considers the input valid if at least one of its computation paths
Okay.
leads to an accept state.
Okay.
It's like saying, as long as at least one of our explorers finds the treasure, we're good.
That's fascinating. Seems like NFAs would be much more powerful than DFAs,
It seems that way.
since they can explore so many possibilities.
Yeah.
The source material also mentions that any NFA can be converted into an equivalent DFA.
Yes.
How is that even possible?
That's a really insightful observation.
Yeah.
And it leads us to a fundamental concept in the field of computation.
Okay.
It turns out that while NFAs offer more flexibility in their design,
Right.
they don't fundamentally increase the types of problems that can be solved by finite automata.
Okay.
We can always find a DFA
Right.
that accomplishes the same task as any given NFA.
So they're equivalent in terms of their computational power.
Exactly.
Okay.
The conversion process involves creating a DFA where each state represents a set of states from the original NFA.
So you're grouping together states from the NFA to create a DFA that essentially simulates its behavior.
Exactly. It's like taking all those branching paths in the NFA and consolidating them into a single, more structured map in the DFA.
Right.
Even if that map ends up being a bit more complex.
This is all really making me think differently about how computation works.
Good.
At a fundamental level.
Yeah, it's really interesting stuff.
We've covered a lot of ground already, from simple automatic doors to the formal definition of finite automata
Right?
and the intriguing difference between DFAs and NFAs.
Yeah.
Where do we go from here?
Well, we've only just scratched the surface of the world of finite automata. There's so much more to explore,
Okay.
including a fascinating feature of NFAs
Okay.
called epsilon transitions.
Okay.
That adds even more flexibility to their design.
Epsilon transition sounds intriguing.
They are.
I'm ready to dive even deeper into this world of computation.
Great. Let's continue our exploration in the next part of this deep dive.
All right, let's pick up where we left off. Last time we were starting to unravel the mysteries of non-deterministic finite automata,
Right.
those NFAs that can explore multiple computational paths at once.
Yeah, they are quite intriguing, aren't they?
Yeah.
We were about to delve into a particularly interesting aspect of NFAs,
Okay.
epsilon transitions.
Epsilon transitions, the name itself sounds mysterious.
It kind of is, yeah.
It's like we're about to enter some hidden dimension of computation.
In a way, you're right.
Okay.
Epsilon transitions allow an NFA to change states without consuming an input symbol. Think of it like a secret passageway in a maze that lets you move to a different location without actually taking a step.
So the machine can jump between states without needing any external input to trigger the change.
Exactly. These epsilon transitions might seem a bit strange at first, but they offer a remarkable amount of flexibility when designing NFAs. They allow us to represent complex relationships between symbols in a string in a more elegant and concise way.
Can you give me a concrete example of how this might work?
Absolutely.
Okay.
Let's say we want to build an NFA that accepts any string that contains the sequence ab, but doesn't necessarily start or end with that sequence using epsilon transitions. We can create a branch in our NFA that waits for the ab sequence to appear anywhere in the input string. Once it detects that sequence, it can transition to an accept state through an epsilon transition, regardless of what symbols come before or after.
So the epsilon transition allows the NFA to essentially skip over any irrelevant symbols and focus on the crucial pattern we're looking for.
Exactly.
That's pretty clever.
It is. And it highlights how NFAs, with their branching paths and epsilon transitions, can often be more intuitive and easier to design than DFAs for certain tasks. They give us a more expressive way to capture complex patterns.
Okay, I'm starting to see the power of these epsilon transitions. But you mentioned earlier that any NFA can be converted into an equivalent DFA. Does that still hold true even with these epsilon jumps?
That's an excellent question, and the answer is yes. Even with epsilon transitions, we can always find a DFA that accomplishes the same task as a given NFA. The conversion process involves a technique called the epsilon closure.
Epsilon closure. That sounds like a mathematical spell.
Yeah, it does a little bit.
What exactly does it do?
Essentially, the epsilon closure helps us identify all the states that can be reached from a given state through a series of epsilon transitions. It's like mapping out all the secret passageways connected to a specific location in our maze analogy.
So by using the epsilon closure, we can group together states from the NFA that are interconnected through these epsilon transitions and create a new state in the DFA. That represents that entire set of possibilities.
Precisely. And by repeating this process for all the states in the NFA, we can construct a DFA that mimics its behavior perfectly, even if the resulting DFA ends up with more states than the original NFA.
This whole concept of converting NFAs to DFAs is really making me appreciate the deep connections between these seemingly different types of finite automata.
It's a fundamental concept in the theory of computation. It highlights the fact that while there are different ways to model computation, there are also underlying equivalences between those models.
Speaking of different models, I remember the source material mentioned that finite automata are just one type of computational model. Are there others?
There are. Finite automata are foundational, but they have limitations in terms of the types of computations they can perform. For more complex tasks, we need more powerful models. Like push-down automata.
Push-down automata.
And Turing machines.
Push-down automata and Turing machines? Those names sound even more exotic than finite automata.
They do.
What can they do that finite automata can't?
Push-down automata have an additional feature, a stack, which allows them to keep track of information in a more structured way. Think of it like a stack of plates, where you can only add or remove plates from the top. This simple addition allows push-down automata to handle problems involving nested structures, like matching parentheses in a mathematical expression.
So the stack acts like a temporary memory.
Yeah, you could think of it that way.
That helps the machine keep track of its progress through nested structures.
Exactly.
That's pretty ingenious.
It is. And then there's the Turing machine, which is considered the most powerful theoretical model of computation.
The Turing machine sounds like it's in a league of its own.
It is pretty amazing.
What makes it so special?
A Turing machine has an infinite tape that it can read from and write to.
Wow.
Giving it unlimited memory.
Okay.
It also has a head that can move back and forth along the tape, reading and writing symbols.
Okay.
This seemingly simple setup turns out to be incredibly powerful.
So with its unlimited memory and the ability to move back and forth through the data, the Turing machine can perform any computation that's theoretically possible.
That's the incredible thing.
Wow.
The Church-Turing thesis, a fundamental concept in computer science, posits that any problem that can be solved algorithmically can be solved by a Turing machine.
That's mind-blowing.
Yeah.
It means that this theoretical model encompasses the entire realm of computation.
It does.
Wow.
And it has profound implications for our understanding of what computers can and cannot do.
We started this deep dive by asking, what is a computer?
Right.
It seems like the Turing machine provides a pretty comprehensive answer.
It does, at least in a theoretical sense.
Right.
Of course, real-world computers are not Turing machines.
Right.
They have finite memory and other limitations.
Yeah.
But the Turing machine provides an abstract framework for understanding the fundamental principles of computation.
It's like a blueprint for the ultimate computer.
Yeah, a good analogy.
Even if we can't quite build it in its purest form.
Exactly. And it helps us appreciate the remarkable power and versatility of computation, even with the limitations of real-world machines.
This is all incredibly fascinating.
It is.
We've journeyed from the simplicity of automatic doors to the profound implications of the Turing machine.
Right.
And we're still just scratching the surface of the theory of computation.
There's always more to explore in this field.
Yeah.
But for now, let's take a moment to reflect on what we've learned about finite automata and their place in the broader landscape of computational models.
That's a good idea. Before we wrap up, is there anything else about finite automata that we should touch on?
One thing we haven't discussed yet is the concept of regular expressions.
Regular expressions. I've heard that term before, but I'm not quite sure what they are.
Essentially, regular expressions are a way to describe patterns in text or strings of symbols. They use a special syntax that allows you to specify things like any character, a sequence of digits, or a string that starts with a vowel.
So it's like a shorthand for describing the types of patterns that our finite automata can detect.
Exactly.
Okay.
And there's a beautiful connection between regular expressions and finite automata. For every regular expression.
Yeah.
There's a finite automaton that can recognize the pattern it describes, and vice versa.
That's a remarkable connection.
It is.
It means we can use these two seemingly different tools interchangeably to represent and manipulate patterns.
It does, and it makes regular expressions an indispensable tool in many areas of computer science, from text processing to programming language design.
Well, this deep dive has been a whirlwind tour of the world of computation.
It has.
We've explored finite automata in depth, touched upon more powerful models like push-down automata and Turing machines. And even glimpsed the world of regular expressions.
Yeah, we've covered a lot of ground.
I'm starting to see computation everywhere now.
I told you.
From the apps on my phone to the traffic lights on the street.
That's the beauty of it.
Yeah.
Once you start to understand the fundamental principles of computation, you see them reflected in so many aspects of the world around you.
This has been an incredibly enlightening journey, and I'm eager to see where it leads us next.
I'm sure there are many more exciting discoveries ahead.
Last time we explored epsilon transitions and even touched on more powerful computational models. Like push-down automata and Turing machines.
Yes.
It's amazing how far we've come from those simple automatic doors.
It is remarkable how such a foundational concept can lead to such complexity. But even with all this talk of abstract models, it's important to remember that finite automata have real practical applications all around us.
You're right. I'm starting to see them everywhere now. From vending machines to the pattern recognition software. That helps filter spam emails.
Exactly. And those are just a few examples. Finite automata are used in a wide range of fields. From natural language processing to bioinformatics.
Wow.
They're a versatile tool for any task that involves recognizing patterns or sequences.
Speaking of real-world applications, I remember one of the sources mentioned using a finite automaton to control a toll gate. Can we revisit that example?
Of course.
I'm curious to see how it works in more detail.
The toll gate example is a great illustration of how finite automata can be used to model a real-world system with specific rules and desired outcomes.
Yeah.
Let's say the toll for a particular gate is 25 cents.
Okay.
Our goal is to design a machine that can accurately determine whether a driver has paid the correct amount.
So it's like a digital version of a human toll booth operator.
Exactly.
But instead of visually inspecting the coins, it's using the principles of finite automata to make its decisions.
Precisely.
Okay, cool.
The machine starts in a state representing 0 cents received. Each coin inserted by the driver acts as an input, triggering a transition to a new state that reflects the updated total.
So if the driver inserts a nickel, the machine transitions to the 5 cents state. Then if they insert a dime, it transitions to the 15-cent state, and so on.
Exactly.
Okay.
The machine keeps track of the cumulative total, not the specific sequence of coins inserted. And once the machine reaches a state representing 25 cents or more, it signals that the toll has been paid, and the gate opens to allow the car to pass through.
It's such a simple yet elegant solution.
It really is.
It's amazing how something as abstract as a finite automaton can be used to control something as physical as a toll gate.
It is. And one of the things that makes this approach so effective is that it requires very little memory.
Right. We touched upon that earlier.
We did.
But can you remind me how this toll booth controller can operate with such limited memory?
Certainly. The beauty of finite automata is that they only need to remember their current state, not the entire history of inputs. In this case, the machine only needs to distinguish between 6 different states, 0 cents, 5 cents, 10 cents, 15 cents, 20 cents, and 25 cents or more. It doesn't need to store every single coin denomination, just the cumulative total, which is represented by its current state.
That's why it only needs a few bits of memory.
Exactly.
It's like a minimalist approach to computation. Only storing the essential information needed to make a decision.
Exactly. And this efficiency is one of the reasons why finite automata are so widely used in applications where resources are limited. Like embedded systems or even some aspects of operating system design.
This entire deep dive has been a fascinating journey through the world of computation. We've explored the intricacies of finite automata, touched on their more powerful relatives, and even glimpsed how these abstract models are used to solve real-world problems.
Absolutely.
What stands out to you as the most significant takeaway from all of this?
For me, it's the realization that computation at its core is all about manipulating symbols and states according to rules. Whether it's a simple finite automaton controlling a toll gate or complex Turing machines simulating the universe. The underlying principles are remarkably similar.
That's a powerful insight. It makes me wonder what other applications for these principles we might uncover in the future as our understanding of computation continues to evolve.
It's an exciting time to be exploring the world of computation.
It is.
Who knows what new discoveries await us just beyond the horizon.
Well, I'm definitely feeling inspired to keep learning and exploring.
Good.
Thanks for taking us on this incredible deep dive into the theory of computation.
It's been my pleasure. I hope this deep dive has sparked your curiosity.
It has.
And given you a new appreciation for the beauty and power of computation.
It certainly has.
Excellent.
And to all our listeners out there, keep those computational gears turning. And we'll see you on our next adventure into the fascinating world of computer science.
See you then, Susan.